All right, we are going to discuss a special type of intermolecular force known as hydrogen bonding, which is particularly strong. So this is going to be very good at bringing two different molecules together. The perfect example of this, I don't know if it's perfect, but a typical example of this is the hydrogen bonding that occurs between two water molecules. So I'm just going to draw two water molecules here like this. And the way you know that hydrogen bonding occurs between two molecules, we're going to call this one up here molecule 1 and this one down here molecule 2, is you need on molecule 1, the first criteria, molecule 1, you're going to need either an NH bond, which I don't have in water, an OH bond, which I do have in water right here, there it is, or an FH bond. So we see in molecule 1 that we have that criteria. We have an OH bond. We also have it in molecule 2. The second molecule, in order for hydrogen bonding to occur, is going to need either a nitrogen atom, which we don't have, an oxygen atom, which we do have, or a fluorine atom. If you have these two things, then hydrogen bonding can occur. The molecule with the NH, OH, or FH bond, we call that the hydrogen bond donor. Hydrogen bond donor. So in this case, we're going to have this water molecule be the hydrogen bond donor, and specifically this OH bond is what's going to, actually the hydrogen on this OH bond is what we're going to call the hydrogen bond donor. And then the second one that has the nitrogen, oxygen, or fluorine, that's going to be our hydrogen bond acceptor. So our oxygen atom on our water molecule is going to be our hydrogen bond acceptor. And what we notice is that with these particular atoms bonded to hydrogen, you get a very large difference in electronegativity between the oxygen and the hydrogen, or the nitrogen and the hydrogen, or the fluorine and the hydrogen. So this is going to be quite negative, and this is going to be quite positive. And then on your nitrogen, or your oxygen, or your fluorine, you're either going to have usually one lone pair on the nitrogen, two lone pairs on the oxygen, three on the fluorine. So I can draw these lone pairs in here on the oxygen. And that lone pair is going to be strongly attracted, right? There are electrons there that's going to be strongly attracted to the hydrogen. So you get a hydrogen bond, which I'm denoting as this dotted line here between the two. And this can happen with a whole host of different compounds and interactions. So for example, if we take acetone, draw the Lewis structure for acetone here. We see that acetone has an oxygen atom. Now it does not have an NH, an OH, or an FH bond. It has CH bonds. So let's check this out. Our acetone, it does not have an NH bond, it does not have an OH bond, and it doesn't have an FH bond. So acetone cannot act as an H bond donor. However, it does have an oxygen atom here, and so it can act as an H bond acceptor. So if we have a water molecule interacting with acetone, acetone does have an OH bond that can act as a hydrogen bond donor to oxygen as the hydrogen bond acceptor. And so we see that water and acetone can hydrogen bond to each other. We're going to take a couple molecules here. Water, ammonia, HF, and methane. And we're going to see, well, we've already seen how water can hydrogen bond to itself. So here's a water molecule. Here we have an OH hydrogen bond donor and oxygen on the second water molecule as a hydrogen bond acceptor. So we see how water molecules can hydrogen bond to themselves. The same is true for molecules of ammonia. If I draw one molecule of ammonia here and another molecule of ammonia here, we indeed see that we have a hydrogen bond donor, an NH bond on one ammonia, and our hydrogen bond acceptor, so hydrogen bonding can occur between two molecules of ammonia. Same thing with HF. I mean, the molecule, it's HF, it's got the HF bond, so this can be a hydrogen bond donor, whereas another molecule of HF has a fluorine atom. This can be your hydrogen bond acceptor. Of course, this can happen in reverse here in this orientation. Here's an HF, that's a hydrogen bond donor, with a fluorine atom, that's a hydrogen bond acceptor. So water, ammonia, and HF, hydrofluoric acid, they all can hydrogen bond to one another, and that hydrogen bonding is going to cause some strong intermolecular force, some strong attraction between the water molecules, the ammonia molecules, and the hydrofluoric acid molecules. CH3 for methane. Let's try CH4, shall we? Okay. Now we're going to check the same thing with methane. We got two molecules of methane here. And we have neither criteria on either molecule. This methane has no oxygen atoms. It's got no fluorine atoms. It's got no nitrogen atoms. So it cannot act as a hydrogen bond acceptor. It also has, since it doesn't have O, F, or H, of course it doesn't have an NH bond, an OH bond, or an FH bond. So of course, methane can neither act as a hydrogen bond donor or a hydrogen bond acceptor. So of course, methane does not undergo hydrogen bonding. All right, we are going to look at a series of substances. So we're going to look at methane, silicon tetrahydride, germanium tetrahydride, and tin tetrahydride. Note all of these, carbon, silicon, germanium, and tin, are all in the same column on the periodic table, so they belong to a family. So we're looking at a family of compounds here. And we can do that with ammonia as well. We can look at its family with phosphorus trihydride, arsenic trihydride, and antimony trihydride. So these are compounds that are going to look similar to ammonia, as they are in the same family as ammonia. And then we can look at water, hydrogen sulfide, dihydrogen selenide, and dihydrogen telluride. All of these, oxygen, sulfur, selenium, and tellurium, are in the same column on the periodic table. So these are going to have structures similar to water. And then finally, we'll do the same thing with fluorines group, the halogens, HF, HCl, HBr, and hydrogen iodide. Of all these compounds here, the only ones that can hydrogen bond to themselves, we already showed that methane cannot hydrogen bond to itself. We saw that ammonia can hydrogen bond to itself, water can hydrogen bond to itself, and fluorines hydrogen fluoride can hydrogen bond to itself. All these other compounds cannot. And so what we would expect in these particular compounds is that ammonia molecules, water molecules, and HF molecules would have particularly strong intermolecular forces or strength of attractions for one another. While the other ones, of course, are going to have intermolecular attractions, but they're not going to be quite as strong as the others. So what I want you to do is I want you to take a look at this graph. And in this graph, what we're looking at on the y-axis is the boiling point of some various compounds on the y-axis. And on the x-axis, we are looking at what period of the periodic table the central compound, or the non-hydrogen atom, I should say, in the compound belongs to. So let's look at this bottom trace, which is colored purple. You'll see CH4, the molecule down there at the lower left-hand corner with the black carbon atom and 4 hydrogen atoms around it. We recognize that carbon is in period 2, and so we recognize that the boiling point of methane, which has a carbon in the center, which is in period 2, that boiling point is somewhere between negative 130 and negative 180 Celsius. As we move down the column to silicon, down the column to the third period, we see a rise in boiling point as we get to silicon tetrahydride, and that's because silicon tetrahydride is bigger. It's harder to boil larger compounds. The same thing occurs when we go to germanium tetrahydride. It's a little larger, and so the period 4 compound in this group is going to be a little higher still. And then moving up to tin tetrahydride, again we see that the boiling point's a little higher. So we see a linear trend in boiling point as the compounds get larger. None of these compounds display hydrogen bonding, and so we don't see any goofiness in this trend of larger compounds boiling at higher temperatures. But if we look at the other 3 series, the one in blue, which represents oxygen's group, the one in red, which represents the halogen group, and the one in green, which represents ammonia's group, we see the trend for the largest 3 compounds, the period 5, the period 4, and the period 3 compounds show this trend of increasing boiling point as the compound gets larger. But holy cow, look at what happens with water and HF and ammonia. The boiling point of these 3 compounds is anomalously high. It doesn't follow the trend. And this graph shows the impact that hydrogen bonding has on the strength of intermolecular forces in water, HF, and ammonia, and the impact that that has on boiling point. Stronger intermolecular forces, higher boiling point.